Hey everyone, welcome back to AP Precalculus. This is lesson 1.12. Let's get right into it. All right, so here's the bell ringer for today. Pause the video now if you haven't done this already, because I am about to go over the answer. All right, so we have a binomial theorem problem, and we want to use the binomial theorem to expand 2x plus y to the fourth. So the first step is to draw out Pascal's triangle. Once we have Pascal's triangle drawn out, we then want to identify our a, b, and n from this form. So here our a should be 2x, our b should be y, and then our n should be 4. And now you want to find row n in the triangle. So remember, this is row 0, row 1, row 2, row 3, and then this is row 4. So our coefficients should be 1, 4, 6, 4, and 1. Looking at the answer choices, the only ones that have that is C. Everything else kind of looks the same, and so we know C is going to be our answer just from that. But if we wanted to figure out how do we fill the rest of this in, right? Remember, you start with A, so 2x to the power of n, which is 4, and as you move from left to right, you decrease that exponent by 1. And then we have, let's see, here you want to start with b on the other side, which is y, to the power of n, so 4, and decrease the power by 1 until you get nothing. And now this is our answer, and so the one that this matches up with is C, and so this is the binomial theorem in action. All right, so today we're going to be talking not about the binomial theorem, but about transformations. And why do we care about transformations? They're very critical to just understanding functions as a whole, which is a lot of what this class is. We'll study a variety of functions over this year, such as polynomial. We're studying rational functions right now. Next semester, we'll get into trig and even some logarithmic and exponential functions too. All of these different types of functions, they look so different, can be transformed, meaning we either shift them, maybe up or left or right, or we change them, like we stretch them vertically or we reflect it over a certain line. And so we want to just learn how to move functions in a more general sense today instead of dealing with specific functions just yet. So today we're going to be talking about translation. And so just like translating a word, we don't actually change the definition of the word, but we change the language that the word is in. That's what translating a word does. Same thing with a graph, right? If we have a graph, let's say we have a star, and we translate this on an XY plane, that means we may be moving it and changing the location, but we aren't changing the size and shape of that star. That will be later for reflection and dilation. So let's take a look at the vertical translation. This line should actually be like that. This should be f of x, so ignore this part right there. Basically, we're going to have two graphs. We're going to have f of x and g of x here. The way I like to think about it is f of x is going to be our old graph, our original graph. So I'll label those there. And then g of x is going to be our new graph, the graph that results as a shift. So new and new here. So if we have a vertical translation, we take the old graph and we move it up or down k units. Then that gives us a photo of our new graph. So f of x has a vertical translation of k units if it's plus k. All right? So here, this one is shifted down 2 units. So our old graph moved down 2 units will give us our new graph, which is that g graph right there. So let's practice this, right? Given the graph of f, we want to find the new graph after this is shifted up 4 units. So I like to take certain critical points, like here, 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 and here, those 4, and then shift each 4 of those points up 4 units. And then you can kind of connect the dots in the same way. So that would be what this looks like, where we shift this whole graph up 4 units there. All right, now let's see what happens when it's -4, when you shift it down 4 units. So likewise, I take each important point and then shift it down 4 units. Let's see. So that's what that should look like, and then connecting the dots should be like this, where we take this graph and you move it down 4 units there. All right. Now notice how this is a vertical translation, which means that effect, that +4 or -4, when a transformation affects the graph vertically, right? Whether it's moving it up or down, it's going to be on the outside of that function. You kind of have that function in a box, and you have the transformation outside of that box. That's going to be pretty important because that's different than horizontal translation, which is moving a graph left or right. And whenever you affect a function horizontally, you're going to be focusing on the inside of that function box, right? Now f of x becomes f of x minus h. So let's take a look here. This is a horizontal translation where this is our old graph, and then g of x is our new graph. So here, if we have f of x plus 2, right? F of x is our old graph, and then g of x is going to be our new graph, where we move this 2 units to the left. Now, like horizontal translations and horizontal transformations, while they affect the graph on the inside of the function, they also affect the graph in the opposite way that it looks like it should affect the graph. And what does that mean? That means if you have f of x plus 2, a lot of people would expect this plus 2 to move it 2 units to the right. But because it's on the inside of the function, it's actually going to move it 2 units to the left. And so horizontal translation is kind of inverse like that. And that's going to happen anytime you see anything that affects the graph horizontally. It's going to do the opposite or the inverse of what it looks like it should do on paper. Vertical translations are straightforward because it's on the outside. And that's going to be if it's like f of x, right? If we go back to that last example, f of x plus 2, this moves it up 2 units. But f of x plus 2, this moves it 2 units to the left. All right. So here, this is kind of what I was saying. Remember, if g of x equals f of x plus 4, this moves the function up 4 units. But g of x equals f of x plus 4, where the x plus 4 is on the inside, is going to move it left, not right, 4 units. Very important there. And then basically any function that will affect the x values, right, or affect the graph horizontally, either stretching it out, which we'll get to later, or moving it just left and right, which is what we'll basically cover today, will happen on the inside of the parentheses and will do the opposite of what it looks like it should do. So think about that. Just remember, that's something I would commit to memory, is if it moves the graph left or right or affects it like horizontally, it's going to do the inverse of what it looks like it should do, and it is going to happen on the inside of that function. Any transformation that will affect the y values or affect it vertically, moving it up or down, or when we get to it later, stretching it up or down, will affect the graph on the outside of the parentheses, like so, and will do exactly what it looks like it should do. So very, very important there. All right, so now let's practice a little bit of horizontal translation. And so here we have f of x plus 4. This is going to move it 4 units to the left. So I take each point and move it 4 units to the left here. There we go. 1, 2, 3, 4. 1, 2, 3, 4. And then connect the dots. So that should be our newly transformed graph, where this is 4 units to the left. Right here, now we have x minus 4. You might say, oh, that's 4 units to the left. No. Because it's on the inside, it's going to move it 4 units to the right. So be careful on that. Taking this, that's how the graph should look, moving 4 units to the right. All right, and now the final thing that we'll talk about today is reflection over the x-axis. If there is a negative coefficient outside the original function, right? So pretend this function is like your safety box. If there's a negative sign outside, then you're going to flip it because it's outside of that function. You're going to flip it vertically. You're going to flip it over the x-axis there. So for example, take y equals x squared and then y equals negative x squared. Y equals x squared looks like this, right? Just that parabola there. Y equals negative, and then you still have that function x squared. It's not negative x and that whole thing squared. So this is different than negative x squared. We are just putting that negative outside the original function. So it is not that. This is going to flip this graph that was once like this. It was once like that, but now it's going to be like this. And so this is an example of vertical reflection. There. All right. You should do vertical reflections before you do translation. So reflection before translation, very important. Remember that order. Just reflect it first and then translate it. It's also a lot easier, more than likely, to do it that order as well. Right, so example number 3, given that this is the new function is going to be a vertical reflection over the x-axis, find it. So this should be, here's our main points. Whoops, that's kind of sloppy. Let me redraw that. And that would be the vertical reflection there. So this is our new g of x, which is reflected over the x-axis. All right, now we want to reflect it over the x-axis first. Then here we want to move it up 5. And this looks like left 2, but it's on the inside, so it really should be right 2 and up 5. So the first thing I'm going to do is I'm going to use different colors to show each step. I'm going to first graph it in green to show that vertical reflection. There we go. And now I'm first going to move it. It doesn't matter if you move it right or up first, so I'm just going to move it up. There we go. That's a little sloppy. Let me clean that up as well. All right, so that is what our graph should look like after you move it up 5. And then this is going to be the flip. So that says reflect. And now we want to move it right 2. So we're going to take each point and move that bad boy over 2 units. And so that should be our answer. And so in terms of our final product, we can almost erase everything else. Erase all that green there. That would be our final graph. And so what I would recommend doing is when you do it on paper, right, reflect it, do it very light in pencil so you can like erase it pretty easily, and then work off of that to move it up 5 and right 2. Once you have that, erase this graph, like kind of like what I did on the PowerPoint. All right. Now, looking at transformations analytically. When we look at transformations analytically, we want to make sure we are changing something that impacts the initial x value, or if we want to see if it impacts the y value. For example, this vertical translation is much different than this horizontal translation. Let's take this function 2x plus 3, and let's take a look at moving it 6 units down versus 6 units to the right. So f of x minus 6 is just 2x plus 3 minus 6, which is just g of x, I should say, is equal to 2x minus 3. So that's our answer there. And then we have h of x equals f of x minus 6. This is going to be h of x will equal 2, and now wherever we see x in the equation, we replace it with x minus 6. So this should be 2x minus 12 plus 3, which simplifies to 2x minus 9. So that should be h of x there. All right, so notice how these two equations are very different based on whether you're just subtracting 6 from the whole function or you are plugging in x minus 6 into any time you see x. So here, example 4, given this function, I'll let you pause the video now, try this on your own, because I'm about to go over the answers here. So here we have g of x equals f of x plus 4, which is equal to f of x is just x squared minus 3x plus 2 plus 4, which is x squared minus 3x plus 6. Here, g of x equals f of x plus 4, which is x plus 4 squared minus 3 x plus 4 plus 2. Foiling this out, you should get x squared plus 8x plus 16 minus 3x, so foil this out as well, minus 12 plus 2. And this is what you get when you FOIL out x plus 4 and x plus 4. This then is going to be x squared. 8x minus 3x is plus 5x. And then 16 minus 12 is 4, plus 2 is 6. So that's going to be our answer there. So notice how these two are very different because of the transformations in it. All right, so now we want to take a look at transformations numerically. So that's really saying through a table or potentially a shifted point. All right, so ask yourself, basically what you want to do is if you see a transformation happen to an entire table, you want to ask yourself, what is actually happening to the x and the y values of this table? So let's take this 3-point table right here. I just made it up. And then let's say we have this transformation right there. G of x equals f of x minus 3 plus 2. Here we have what transformations will happen, right? That plus 2 is going to move it up 2 units, and that x minus 3 should move it right 3 units. So what does this really mean? What this means is that we are moving it up 2, so all of our y values should be shifted up 2 units. So the first transformation is take any y value and add 2 to get our new y values. So 4 plus 2 is 6, that looks good. 5 plus 2 is 7, 6 plus 2 is 8. Now we have our x values and we're moving it right 3, right? If you have 1 as an x and you move it right 3, you're going to then add 3 to these to get 4, 5, and 6. And so this is our transformed table like so. So looking at it numerically, given this table, and then g of x is f of x plus 2, find g of 2. Here, there's multiple ways to do it. The first way is looking and seeing that this is shifting your y values. You're moving it up 2. And so we can just add 2 to all of our y values here. So this is g of x is equal to f of x plus 2 is just 23, 14, 20, 16, and 12. And then g of 2 is just going to be 12. The other way that you can do it is literally to find g of 2, so 12 should be your answer, equals f of 2 plus 2, which is 10 plus 2, right? So you could just actually just plug that point in and then evaluate it from there. Same thing here. Let's find f of x minus 2 plus 1. So this moves it right 2 and then up 1. So we can add 1 to each of our y values here. So 9, 1, negative 11, negative 19. And then we move our x values over 2 to the right. And so these should be our new coordinates when they're transformed. So to find 4, g of 4, this goes with 1. So 1 should be our answer here. You could also do it a different way by just taking the original table, and both of these will get you the same answer, taking that original table and then plugging in 4. So g of 4 equals f of 4 minus 2 plus 1, which is f of 2 plus 1, which is f of 2 is 0, plus 1, which is just 1, and you get the same answer there. We basically are just doing it inside the equation versus transforming every x and y value. Whichever way works best for you, totally fine. Right, so now example 6, we have a graph that is transformed like so. Draw the transformation on the same graph. So here, we're moving it up 2 with that plus 2, and then with that 1, we're moving it left 1. So I'm going to take each point and move it left 1 and up 2. So here, that is where that point should be. This point as well, right here. All right, so let me erase. So this is kind of messy, so let me kind of clean this up a little bit, right? So cleaning up my points, right there, right there, right there, and right there. So those are my 4 points, and now you just want to connect them using straight lines, and that should be our transformed graph. Example 7. We have a table of values. Which of the following gives the function f, where it's a transformed function of g? So what we want to do here is we want to ask what transformations are happening. So we're shifting it down 4, right? And then that x plus 2 is shifting it left 2. So our x values are shifting left 2. So now our new x values should be negative 1, 0, 1, and 2. So the ones that correspond with that should be a and b. So we can eliminate c and d. And then our y values are shifting down 4. So we want to subtract 4 from each of those. So negative 1 minus 4 is negative 5. 2 minus 4, negative 2. And the one that matches up with y value-wise out of a and b is a. So a is our correct answer there. Example number 8. Which of the following is a transformation from f to g? And so here, I'm going to take 1 point and see how that 1 point moves. So I'll take the n there. Here, the coordinate is negative 2, comma 1. And then this coordinate is at negative 4, comma negative 2. So I see the x coordinate, if I plot that here, right, this is where that moved. So we moved to the right 2 units, or sorry, to the left 2 units. So 2 left. And then we also moved down 3 units. So 3 down. So that 3 down, let's take care of that first. Out of our transformations, it should be minus 3. So you can eliminate b, and you can eliminate d. And now the 2 left, it should be x, not minus 2, but x plus 2. So c should be our correct answer, and you can eliminate a. So that is our answer for example number 8. All right, day 2. Here's the bell ringer. Pause the video now because I'm about to go over the answers. So we have just an equation, 3x minus 5, and we want to see a horizontal translation of 4 units. One thing to note is that this means our new function, we'll call it just an arbitrary like f of x, is going to be, if this is k of x, it should be k of x minus 4 is that horizontal translation of 4 units. So even though it doesn't say left and right, because it's always inverse, it's going to be k of x minus 4, not k of x plus 4, because this shifts it 4 units to the right, which is when if it said minus 4, then this would be k of x plus 4, all right? But it doesn't say that, so we don't have to worry about that now. Now we want to evaluate this, so this is just 3x minus 4 minus 5. And then we don't even need to simplify it. This matches up with B. The explanation, it's an additive transformation, right? Which is just shifting it up and down or left and right. That results from subtracting 4 from each input value of x, which is what we have here. So that's perfect. So B is the correct answer for our bell ringer. Right, now, we talked about how you should always do reflection before translation. However, we're adding in a new character, dilation. And so this is the order in which you should make any transformation, which is reflection, dilation, then translation. I remember the acronym RDT. And if you remember iCarly, if you ever watched that show, you guys may be too young. If you saw random dancing time, like when they would have that random dancing segment, I remember just this acronym, random dancing time, for reflection, dilation, and then translation in that order. All right, so just as a refresher from what we learned about transformations, if we have something that affects the graph vertically, right, up or down, it is going to occur on the outside of the parentheses, so like f of x plus 2, and it is going to be straightforward. And do exactly what it looks like. So this plus 2 is going to shift it up 2 units. If we have something that affects the graph horizontally, it's going to occur on the inside of the function, and then it's going to do the inverse of what it looks like it should do. So this will actually move it 2 units to the left. And so if you know those, you should be good for today's lesson. And so this is pretty much everything I just said on the previous slide, so I'm not going to necessarily go over it, but remembering this will really help for not just today's lesson, but we'll cover transformations again, so just being able to learn transformations a lot easier in the future by just remembering these few things. All right, so let's talk about vertical dilations. Let's say you have a transformation, g of x equals maybe, let's say, negative 3 of f of x. Remember, this is on the outside of that function, so it's going to affect the graph vertically, where if you have an equation or a graph like this, let's see what happens with this transformation here, right? Just as a very broad example. The first thing is, if this number is negative, flip it over the x-axis, so this should look like that. The next thing you want to do is, because it's outside, it's going to affect it vertically, which means it's going to be straightforward. So if it's 3 is that number out there, then you want to stretch this out by 3. So take each point, count how many units away it is. So let's say, and this is just an example I'm making up, that this is 2 units away. Then you want to count 6 units away here, and that should be your new coordinate. So this might be what this looks like here, where this is now a stretched out version like that. All right? Your x values will stay the same for if it's just a vertical dilation. Obviously, we can add multiple transformations together, but vertical, when you're stretching it vertically, keep your x values the same. All right, so let's practice here. Here we have a graph, and we want to stretch it out by 2. So I take this point right here and then count it as 3 units away. So if I stretch it out by 2, the new point should be 2 units away there. This point is 0 units away, so it's going to stay 0 units away. And then this is right there. This point is 2 units away, so its new location will be 4 units away, and then 0. And then that should be my new graph. Here now we're stretching it in by 1/2. So this point is 3 units away from the x-axis. So the new point is going to be half that. So maybe 1.5 units. Those are on the x-axis, so they're going to stay there. And then this point's 2 units away, so it's going to stay 1 unit away because we multiply that by 1/2. So that's just kind of like compressing it by a factor of 1, or vertically dilating it by a factor of 1/2 is what we should say there. All right. Now horizontal dilation, pretty similar, except this time if you have a graph here, let's say we have this function here, you're going to be horizontally, so dilating it or stretching or compressing it over the y-axis. So basically what this looks like is, let's say this is that was f of x, and now you have g of x equals f of, we'll go 2x just to keep it easy. Because it's on the inside, it's not going to stretch it out by a factor of 2. It's actually going to compress it by a factor of 2, or like mush it in 1/2. So the way we do it is we take every point and look at the distance from your y-axis and then cut it in half if this is a 2 out in front. And so this graph should look a little something like that. Now, if it was g of x equals f of 1/2, what would that look like? That would be, so let me just make this clear. Whoops, I think I might be confusing some people with the colors. So here, if we have that blue function there, that blue function should be what g of x equals f of 2x looks like. And then let's say we have a purple function, g of x equals f of 1/2 x. What does this look like? This is where you take this and you take the distance here and then you essentially double it. So you'd be stretching it out by a factor of 2. That's what this function should look like here, whereas this blue function should look like that blue function there. Hopefully that makes more sense now. And then also, if this is negative, that number on the inside, flip it over the y-axis. You won't really see that a whole lot in this class, but you could come across it as well. All right, so horizontal dilation here. We want to take this graph and compress it because it's 2, so we're going to push it in 2. So here, this is 4 units away, so the new point should be 2 units away. This is 2 units away, so it should be 1. This is on the y-axis, so it's going to stay there. And so this graph should look like that. Here, because this is 1/2, we are actually going to stretch it by its reciprocal by 2. And so this is 4 units away. The new one will be 8 units away. This is 2, so it should be 4. This stays the same, and then this should be 4. So this should be that graph there. Right? And now we have negative x, so we just want to flip it over the y-axis. So this point will stay the same. This point will go here. This is 3 units away, so that's going to go here, 1, 2, 1. And then just kind of reflect it like so. All right. Now, vertical and horizontal dilation, this is just a refresher. Vertical happens on the outside. Horizontal dilation happens on the inside. Vertical, pretty straightforward, right? -2, you stretch it out 2 units. Horizontal is going to be, in this case, they just have -1 on the inside, so you just flip it over the y-axis there. And then this is -2, so this should be, each thing is 2 units further out. So, yep, that looks good there. This is just a lot of what we went over, so nothing new with this. Example number 3, given the graph of f, write the transformed function. So remember r dt. So there's no reflection here, so that's nice. But we do have to dilate it by a factor of 3. So I'm going to take each point, and then we're stretching it vertically 3. So this should be right there. This should be right here. And that should be that graph. And now, because it's +2, now we want to do the translation and move each point up 2 units. Let's see here. And now what I'm going to do is I'm going to erase this blue line. We don't need it. And just connect these. And that should be our transformed function there. Right? Now we have a lot. So let's do the order that we need to. So r dt. So let's first do the vertical reflection by reflecting it over the x-axis. There we go. Now let's do the dilation. And so this is a 2 on the inside, so we're going to compress it by a factor of 2, or by a factor, or we're going to horizontally dilate it by a factor of 1/2. So this is 3 units away, so this should be 1.5. This is 1 unit away, so this should be compressed, so this should be 1 in there. This is 1 unit away, so this should be right here. And then that's 3 units away and 2 units away, so this should be like right there. Drawing that is going to look like this. I'm going to erase the red right now. There we go. And now our final transformation is moving this to the left 3 and up 1. So this is around 1 1/2. So 1, 2, 3, and up 1 should be right there. This is -1/2 up 2. So 1, 2, 3, up 1. So that's where that's going to look like. And then right there. All right, so 1, 2, 3. Yep, that looks good. This should be around 2 units away, so right there around. And then this should be 1 unit apart, so roughly around there should be our new transformed function. This may not be perfect, but it's okay. You get the gist. And so it should be like that. That should be our transformed function. Now, obviously, this has a lot of steps. You will never need to graph these on an AP exam, but you may see a multiple choice question where it's like, which one is the transformation of this? And then it gives you 4 answer choices. So like, while you will never actually be graded on your graphing, you may need to graph it to like answer a multiple choice question. All right, algebraically, pretty similar. Here, let's just work through example 4. So this is 2 times our f of x, our function, which is x squared minus 3x plus 2, and then plus 4. So just make sure you distribute the 2. And then you still have that plus 4 in the end. And we can simplify this to get this is our function. If we do the same thing here, g of x equals 1/3 times f of x plus 2. So this is 1/3 times 6, and then instead of x, x plus 2. And so let's simplify this. One third times 6x plus 15, which then dividing each term by 3, you should get 2x plus 5 as your answer there. All right, numerically, this is pretty similar as well. Think about what are you doing to your x and your y values here. And so what you want to do here is let's just find g of 1. This is 5 on the outside, so it's going to multiply your y values by 5 and subtract 1, but we can just plug it in, so let's do that. So g of negative 1 is equal to 5 times f of negative 1 minus 1, which f of negative 1 is 12, right? So this is going to be 5 times 12 minus 1, which is 60 minus 1. So we should get 59 here as our answer. And this one, find g of 2. So g of x equals f of 3 times 2 minus 1. Whoa, lots of parentheses. And then plus 2 on the outside. Let's simplify that a little bit. F of 3 times 1 plus 2, which is just f of 3 plus 2, which f of 3 should be 8 plus 2, which is 10. So that should be our answer there. All right. Now, example number 6. The functions f and g are defined for all real numbers, such that this is the transformation. Which of the following is true? So I see that plus 1. That's going to move it up 1. So a vertical translation of plus 1. So we can eliminate b and d. Then I also see the 2x. This is going to be a horizontal dilation. So we have that. And then remember, it's not by a factor of 2. It's going to be by a factor of 1/2 because it's on the inside and it does the inverse of what it looks like it should do. So in this case, just taking the reciprocal, so C is our correct answer here. Example 7. Here we have f and h. Which of the following could be the transformation from f to h? So looking at this, I'm trying to see what do we do to our x's and what do we do to our y's. And so our x values, I see, is it changes from -4 to -8. 0 stays at 0. 2 goes to 4. 5 goes to 2. So you take your x values and you multiply it by 2, right? You times it by 2. And so where does that happen? What we want to do is that's going to affect it, the x values, horizontally. So it's going to be on the inside. And it's not going to be by a factor of 2, right? It's going to be by a factor of 1/2. So it should be b, should be our answer there. Or it could be C, but here we don't change the sign, so it should just be B is our correct answer. And if we look, we have 1, 2, 3, and 4, and now our y values are changing from 1, 2, 3, and 4 to -1, -2, -3, -4. So because our y values are turning negative, B is also our correct answer here. And then finally, example number 8, the final question here. Which of the following is the transformations from here to here? So looking at this, I see that we don't move it up or down, right? And all you're doing is you're moving each point in by 1/2 the distance. So that's what we're doing there. And so we are horizontally dilating it, or horizontal dilation, by a factor of not 1/2, but by a factor of 2. So A should be our answer there. All right, so make sure you're aware the factors isn't really always going to be what you're multiplying it by, because technically you take the distance, right, this distance here, and you multiply it by 1/2 to get that new distance. So with horizontal dilations, you're going to take the reciprocal number to get your distance that you multiply it by to find your new distance. All right. If you have any questions, please come see me in office hours, and I will see you guys later. Thanks.